Okay, here we are. This is the next lesson. Okay, it's about potential functions. Let me first start presenting the session, the potential function session, and then at the end of the class, if we have time, what we can do is the exercise that I just upload to the Moodle, in which we solve, in which I ask you to solve some back algorithms, basic back algorithms with some environment. Then I can do it here all together. Then you know that you have the correct. Okay, but let's start now that probably you are fresher with a little bit of theory. Let's hope that Pedro Ridao has not made you think a lot with all the questions that he always shows. Then let's start. What is the class about today? The class is about potential functions. And how are we going to imagine that? Okay, potential functions are a kind of functions that can be used to do exactly what we are doing all this day. That is moving one robot, a vehicle, from one position to a goal position, from a starting position to a goal position. Just to start, let's assume that the robot that we want to move is just a single point. Then it's x, y. If you remember the other class in which we were explaining a little bit what is the configuration space and the obstacle space and the free space and all this stuff, then a robot here in this lesson, we will imagine that is the simplest thing ever in 2D. It's just an XY point. And the goal then is also an XY position configuration. Okay? Then the idea of a potential function, we can do several analogies. For instance, a simple one is imagine that we have a spring, and we have a spring attached to our robot, and the same spring attached to the goal, and then the spring is pulling towards the goal. However, we don't have only a single spring. In each obstacle, we have also other springs that just, if we get close to this obstacle, then the other springs will push far from the obstacle. Then this is an analogy. Yeah? Another analogy that maybe is even easier to understand is imagine that we have electric charges. Okay, we have here our robot. The robot is charged positively, and we want to reach here the goal that is charged negatively. Then they are attracted. However, if we get close to the obstacles, because obstacles are also charged positively, then the robot tries to move away from the obstacle. Okay. The final analogy that I can imagine about potential functions is that just imagine that this 2D wall that we are always assuming is not completely flat, but it's a kind of bubble, and the goal is exactly at the center of this bubble, in the middle, in the lower part of this bubble, while the robot, when it starts, the initial position, is at the rim of the bubble. Then, just for gravity, the robot will always try to move down until reaching this minimum point. Okay, this is just analogies to understand what we are trying to do today. But in the end, all these analogies, the spring, charges, bubble, whatever, is just to understand that we have a potential function. It's telling us the potential energy that we have at each specific configuration. Okay, and then our robot, the only thing that our robot will be doing is follow this potential function, potential energy function, towards a configuration of lower energy. Okay, it will always start in a high energy configuration and try to reach the lowest energy configuration. And then the function that we are going to use for that is we will have the configuration. In our case, the configuration will be x, y, but here we can have x, y, theta, rho, pga, or whatever configuration you want. And for each configuration, we will obtain a potential value. Okay, it's from n here, a scala of real number, we transform it to a single real number. Okay, that is the potential energy at this particular configuration. And then how the robot is going to follow this configuration, how the robot is going to move towards the lower energy, then just following the gradient. Okay, the gradient is this other function that you have here. And basically, for each configuration, we will do the derivative of the potential function for each particular configuration, and then just follow the lower energy path. Okay? This is the main idea of what we are going to do today. Okay? then let's see some of these potential functions that we will be looking at today. This is the next exercise that you will have to implement in the labs, okay? I think today you have the second lab. The idea is that this first lab is more an introduction to Python and notebooks, and be sure that all of you understand how to program using NumPy and plotting things with Matplotlib. It's not much about robotics, a little bit, but not much. Now the second lab that you will be doing is exactly that. It's implementing these potential functions that we will be discussing today here in class. Okay? We will start for this concept, okay? We will have like three main potential functions. The attractive potential function that will attract the robot to the goal, and you can imagine is the one I've tried to draw here, okay? All the arrows that everywhere that you are in this world, in this environment, they attract you, they tell you to move towards the goal. This is an attraction potential function. Here we don't care about obstacles, we just care about the direction to the goal. Then we have the repulsion potential function, that this is something that we need to compute for the environment, for the specific environment. Every time that we have an obstacle in our environment, we need to compute a repulsion function that moves away from this obstacle. Of course, if we have a single obstacle, it's very simple. If we have plenty of obstacles, then we have to find ways to do that in a convenient way. And then, in the end, our total potential function will be just a combination of these two functions. Okay? If we are able to combine the attractive potential function and the repulsive potential function, we will have a total potential function that wherever we are, in any configuration that we are, we will just check the potential function and the potential functions around this current position and follow the one that has less gradient, will be the one that gets closer to the goal. Okay. Which is the simplest potential function that we have? Probably is this one. It's an attractive potential function when we only consider the distance to the goal. Okay? This is the function that I'm talking about, and if you take the d from q to q goal, means the distance from the current configuration to the goal configuration. This is something, remember, in the back algorithms, we were assuming all the time that we know more or less where the robot is and where the goal is. And therefore, it's easy to compute the bearing towards the goal and also the distance towards the goal. These are the two main things that we need to compute in back algorithms, okay? How close or how far I am from this current position to the goal, and which is the direction to the goal. These are the two only things that we need to compute in back algorithms. Here, it's almost the same, okay? If we more or less know where the robot is every moment, and we know where is the goal, we reach towards the goal, it's normal that we know where the goal is, then we can just compute the distance, and with that, it's enough to compute the attractive potential function. This sign that you have here in front is just an scout, okay? A game, let's say. But here the problem, or how this question works, is that the potential energy increases linearly, okay? With the distance. Sometimes we want that, it's okay, sometimes not. This is what it means. It means that when we're very, very far from the goal, it will pull us quite strong. And the sooner that we are getting closer, it pulls less, until we reach the exact position of the goal in which this potential function is not pulling us at all. Okay, then we stay at the goal that is in the end what we want. A small modification to this potential function, to this super basic potential function, energy function, is just using the quadratic potential function. Okay, that basically we replace the distance by the square distance. Only that. The standard equation, instead of using the k, this gain factor, uses half of this gain factor. But I mean, the main idea here is that we have this quadratic potential function. Then, if we are super close, you know that the quadratic of something that is below 1 is much smaller, while when we are far, then it's much higher. Instead, basically here is, instead of having, if this is the goal, and we start from this position, instead of moving like that, and if we go from the opposite direction, we move like that, no? Starting from here, now we do something like that. It's more the analogy of the bubble that we were talking before than something linear. Okay, but it's almost the same than using a linear function than a quadratic function. It's just this analogy, that we make better this quadratic analogy, and the gradient will be smooth. Okay, then how we are going to implement that? At least how you are going to implement that in your lab. Of course, this is something that can be computed online. I mean, if I know where am I and I know where the goal is, it's super simple just to compute the potential function, the attractive potential function in this particular area. However, as I told you in the first classes, in this first semester, we are going to assume that the world normally is known, okay? That we have access to a map of the environment where the robot is moving. Therefore, this is something that we can compute very simply for this world a priori. What we need for that is not that initial position. We don't care where the robot starts. I don't care if the robot starts here, or it starts from here, or it starts from here. I don't care that. The only thing I care is where is the goal. Okay? The potential function only needs it needs to compute the potential energy from all the environment with respect to the goal, not with respect to the starting position. Therefore, I only need to know the goal, and therefore, if the goal changes, I need to compute again all these potential functions. But if the goal is not changing, I can reuse the same potential function. Okay, then to do that, I will just apply or the linear potential function or the quadratic one and obtain a map. Here it's a matrix in which each state, remember that we work with computers, then we discretize the continuous space into cells, into something that is discrete. For each particular cell, we compute this distance. Here, instead of using one or the other, what we have done is just apply this if here, okay? Basically, what we say is, if the distance between the current configuration and the goal is smaller or equal to some threshold, we apply the quadratic. However, if the distance between the current configuration and the goal is bigger than this threshold, we just apply, and here is the linear minus half of this distance. Okay? Yeah, I don't remember now. Yeah, half of, well, this is this threshold here. This is a fixed value. But basically, it's applying the linear thing, except for this part, to avoid discontinuities. This is just to, when we change from one function to the other, basically what we are doing is we move linear, and at some point, sorry, I need to move it. We need linear, at some point, we move as quadratic and we make it smoother. Then, to avoid a high discontinuity, in the moment that we change from one function to the other, we just apply this term here. Okay? It's the only thing. But in the end, it's two very simple equations that you can compute just using an if and some very simple mathematics, and then compute it. Okay, this works. So imagine that I have a small ball, and I put this ball in any place of this figure. Okay, I can put it here or here or here, and the ball will always go down and reach this position, that is the position with minimum energy, that is more or less, this position belongs to this area here, that is where I've indicated that is my goal. Which is the problem here? That, yeah, here there are no obstacles, but in reality there are obstacles, and we need to fix that. Okay, to avoid the obstacles, what we are going to use is the repulsive potential function, okay? This is a super simple lesson, today no worries at all. The repulsive potential function, again, uses this conditional structure, okay, that depending if the distance, however, this capital V here is not, you remember the small d was the distance between my current configuration and the goal configuration. This says only distance with respect to your current configuration. Distance with respect what? With respect to the goal, with respect to an obstacle. The capital D will represent distance with respect any goal in the environment. Okay? Then, if the distance, if I'm able, we will see later how we do that. But if I'm able, imagine right now, to compute the distance from my current configuration Q to all the obstacles in the environment. Okay? Imagine that we are able to do that. Then, if after doing that for all the goals, the minimum distance that I obtain is smaller than this threshold, this is again a threshold, then I apply this function here. And basically, this function here again is a quadratic function, then you could do this smooth part. This is this threshold, this Q star, you have it here. You have the Q star is here, and you see that this is smooth, okay, because this is quadratic, basically, yeah? However, if we are farther, if the distance to any possible obstacles is bigger than this threshold, this Q star vector, we just say G. Then the recursive function is not active, it does nothing. Okay? What we will end up, if I apply this equation to this map, to the map that we present here, what we obtain is something like that. Okay? Of course, the taller this map is, will be configured with this eta here, half eta that we have at the beginning of the equation. This will tell us how tall this equation is, but what is interesting to see here is that around the obstacles, we have this smooth, of course, again, here I discretize the environment, then everything is discrete, and the cells are maybe not as small as they should be, and then you can see that everything is smoother, and if I get close to the corners, to the obstacles, I don't find an edge that is 90 degrees, no, I find something that is smooth, that allow me maybe get a little bit closer, but not too much close to the real obstacle. Okay? This is just the definition of this dq, and the q star, that is the threshold, and the eta, that is this positive constant that controls the strength of the repulsion, how tall is this graphic. Okay, then if I'm able to compute the attraction function, and I am able to compute the repulsive function, I can just add them, add number by number. Of course, you have several gains here that you have to tune a little, depending how big is your environment, how big are your obstacles, the queues, etc. There are several things that have to be tuned, but whenever you have tuned that, you obtain something like that. Okay, and here it seems that now if I throw a ball here, then this ball maybe will go here, then we will be moving around, and then it will reach approximately this position, that is, well, maybe even a little bit down, no? Maybe around here, no? That is probably the position of minimum energy. And if I throw it through the middle, then it will throw through the middle, and maybe go here, and end up. Okay, this is more or less the theory, and this is what we expect to happen. We will see that not always happens. Okay, it's clear, and with this map, I think it's clear that here we will have some local minimums, and then we need to see how we can fix that. Because if we have a local minimum, we will not reach the minimum energy area. We will just get trapped in some local minimum. This is something that we need to solve. But for the moment, imagine that we are happy and that this is working, and that if we just compute the traction and the repulsive, we can add them, compute the gradient, and go down. Okay, for the attraction, I think it's pretty simple. We just need to measure distances. Here there is nothing else I have to explain to you. However, for the repulsive, I told you that we have this. Wait, sorry, I don't know what I've done. Yeah, make a big zoom. For the repulsive, we have this d of q that maybe it's not so simple to implement that in code. Okay, you will have to implement all this in code, and then how I can compute the distance to all possible obstacles. We know that we have a wall, that this wall maybe has a list of obstacles or q obstacles. We can define these obstacles maybe as cells, maybe as circles, whatever, no? But in the end, we need to find this function that minimizes, computes the distance for all obstacles from the current configuration Q, and then returns us the minimum value, okay? We need to find a way to do that. Then, let's see how we can do that. No? In the repulsive potential function, we need to compute this distance, this to determine the collision risk, as here I explained. And then the idea is, now see that here I changed the capital D by a lowercase d, basically because I'm only checking the distance, the minimum distance, with respect to the obstacle I. Okay, here I am only caring about obstacle I from my current position, from the Q position. Then if an obstacle has this shape, imagine this square or squarish shape, okay, the distance with respect here, maybe the minimum one is here, but if I'm in this position, the minimum one will be this one. If I'm here, the minimum one probably will be this one, etc. Then I need to be able to compute the minimum distance to any segment or any portion, this C, okay, from this obstacle. And this I have to do it not only for the obstacle I, Q obstacle I, but for all the obstacles in the environment. Okay, then here it's not so simple. Of course, whenever I have that, if I'm able to do that, if I'm able to compute this distance, what I will be able to do is then just subtract from the minimum point the current configuration and the point that is the minimum, the closest part of this obstacle to our current configuration. We can subtract that and then divide for this distance, that is basically this distance, and what we will obtain, imagine that I have here, this is obstacle 1, then I'm here assuming that I'm checking this with respect to obstacle 1, what I will obtain is a repulsive vector with respect to this obstacle. Because I divide by the distance, this will be unitary always, okay? Then if I do the same for the obstacle 4, then I will have another repulsive vector around here. And maybe I do it also for obstacles 2 and 3, or maybe not because they are too far. And because they are too far, I don't care. I only care for the obstacles that I'm close. No? Then this is a way in which you can compute a repulsive function just with what you have around. Okay, you just check the obstacles that are closer to you of several thresholds. Imagine this is the threshold. Okay, then all the obstacles that are closer to this threshold, I compute this vector here. I normalize it for the distance, and then the resulting repulsive vector will be then the sum of these two vectors. That will be something like that. Okay, of course. Okay, I'm not very good drawing, okay, but this is just for you to get the idea. This will be the resulting force that we will generate. That will be the sum of all the repulsions that are closer or in a certain threshold. This is a way to do it. Okay, this is all the mathematics that I explained in the drawing, but explain it in words. How we can do that in an easy way online in a real robot? Just using range sensors. Okay? If I use range sensors, imagine maybe with an ultrasonic rangefinder it's so difficult if I have only one, but I can have several of them, or if I have some 2D scanning, that doesn't matter if it's mechanical, if it's LiDAR based, or if I have even a stereo camera or an RGBD that gives me some field of view, then I can compute which are the closest obstacles. Remember in the back that we were also doing similar thing. No, we just check the range of the LiDAR and see the discontinuities. There is an obstacle here, an obstacle here, and an obstacle here. Then we can do something similar. Imagine that we have a 2D LiDAR, that is the simplest one and the one that we will be working more this semester. And then for each one, or for each of the beams that is colliding with one obstacle that is closer to this threshold, okay, maybe it's too close, I should move away of this obstacle, okay, then we can generate one of these repulsive vectors, and in the end just act on these repulsive vectors and obtain a single repulsive vector that is the one that we have to follow, or at least the one that we have to combine with the attractive vector, basically will point us towards the goal and see how we have to. Okay, this is the idea of how you can implement that in real time. But we are not going to implement it in real time. As I told you, we are going to implement it in a map, in a known map, 2D map, that basically is a cell, it's a grid. And to do that, There is a concept here that I never know when to introduce it, but let me do it just now. We can assume that our robot can move only our point robot there. Remember that at the beginning of the class we say that our robot it's a cube that has only the position x and y. Okay, then the robot, it can move or only forward, backward, left, and right. This is connectivity 4. We say that when you are in a cell, in a map, in a cell, you can move to the cell in front of you, the cell behind you, in the left or in the right, or you can move in connectivity 8. In connectivity 8, in addition to up, down, left, and right, you can move in diagonal, okay? Up left, up right, down left, down right. Then you can move to any of the cells around you. When we talk about connectivity 4, we mean that diagonal is forbidden, you can move diagonal. When we talk about connectivity 8, it means you can move anywhere you want around your current position. Okay, then now, remember, we are trying to compute distances with respect to obstacles. This is the part of the recursive function that makes it more difficult to implement. We have explained some tricks to do it online with a real robot, but now let's return to the when we don't want to compute it online, we want to compute it offline in a map and just have the function there, and then we will just pick up the potential function for each specific configuration. It will be much faster than to execute. And let's assume that our vehicle can move or following connectivity 4 or following connectivity 8. Okay, there is an algorithm, I don't know if you have listened them before, that is called the Brush-Fire algorithm. This algorithm can be used for do exactly that, okay? To compute in each specific configuration, which is the distance to the closest obstacle, okay? I think here I have the algorithm itself, yes. Okay, again, I like a lot to put a small part of pseudocode. I think it's good for you, it will help you to implement that later. The idea here is we start with this, we want to generate this distance map, okay, for each configuration, for each cell in this 2D grid, okay. Right now we'll do that. We always try to make the algorithms as generic as possible, okay, but I try to explain you in this more generic way, that is the one that you are going to implement. Then for each specific cell in a grid map, this is what we want to know the distance to the closest obstacle. Okay, I have a list of obstacles. I don't know how the obstacles will be generated. Here, the map, the wall, will be defined again as a grid in which we will have zeros maybe for free space and 1 for obstacles or something like that. Okay, then we will set obstacle cells to 1 and free cells to 0. Okay, this is in this map, in this environment map that I will give you. Then we will create this QL, that all the boundaries around an obstacle will be added in this queue. Of course, if we use connectivity 4 or connectivity 8, the boundaries have to be ones or the others, no? I think everything will be clear when I show the experiment, but imagine that here I have an obstacle. If we are using connectivity 4, then this, and this has to be added to the L. This is too small, No. However, if we are using connectivity 8, I have also to add this, and this to the list, okay? Because the red is the obstacles and the white is free space. Then, the idea is just do this while L is not empty, I just remove one position from L, and for all the neighbors of this cell that I've removed, if the distance is equal to 0, then I set this distance as the distance of the current cell I've removed plus 1 and add these cells into the L. And this will be propagating, expanding until there are no more free cells. There are no more 0 cells. Okay, let's see just a simple exercise, and I think it will be much simpler than trying just to follow the algorithm. Okay, let's try to apply. Imagine that this is our initial environment. okay? We have, in the end, what we want to do is to return the distance to the obstacles. Yeah, there was here a small trick, okay? Return the distance map -1, d -1, okay? You will see why I use this here. Basically, this is the original map that we have, and we just make a copy of this original map. Right now, it says that everything is at distance 0 of the obstacle, except the obstacle itself that is at 0, at distance 1. It makes no sense at all. But this is just to start. The first thing that we will do is to set, let's do it like that. We will set all these elements. This here, I do connectivity, I don't remember in this experiment if I do connectivity 4 or 8. Let's do connectivity 4. I add all this in my configuration file, in my LQ file, LQ. And then for each one of them, I will take the first one, then take the first one and say, okay, this is the distance, this is touching an obstacle, then I will replace this, not by 1, but by 2, and check all the surrounding cells of this one, check all the surrounding cells, and then add this here and this here. This is already in the queue, this is already in the queue, this is already an obstacle, then nothing happens. Add them in this queue, okay? Then I will do the same for that, and I will add here. I will do the same for that. I will add this one, do the same for this one, add this one and this one, then the same for this one, add this one, the same for this one, add this one and this one, the same for this one, add this one, the same. Sorry, no, this is just add the same and the same. Here I don't add anything because already it's there. Once I have done this, I just move to I've done all that have a value 1 in the moment I've added. Now let's see all that in the moment of added in the list. I put a 2, then is this one, then here I have to put 1 plus, remember, You set t plus 1, then because when I've added this element in the list, there was a 2 here, then I have now to add a 3, and I add this one with a 3 in the list, 3, and I add this one, 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 3, and I add all of this, plus this one, and that's all. And then we will move to another cycle, and then the moment in which I have added this in the queue, I add it with a 3, then now I put a 4, there are no neighbors, 4, there are no neighbors, 4, I add this one, 4, I add this one, 4, and I add this one, and 4, and 4. And finally, in the last step, let's do it in orange. In orange, then I will add this one, 5, there are no networks, 5, and this one here, this will be a 6, I don't know, black, a 6, okay? This is the idea. We are adding elements to this queue. When we add elements, we remember, okay, first we add 1s, then we add 2s, then we add 3s, and then we are replacing these elements by the value that they have when we add it, plus 1 for all the rest, okay? I don't know, here when I try to do it, maybe it's the easiest way to see it, with number on top of the other. Okay, here for what I see, I've done it with connectivity 8, you see, because otherwise this will be not a 2, this will be a 3. But it's exactly the same. In fact, maybe it's even clearer with connectivity 8. Here you have the original obstacle, was this one, then all the elements, all the cells that were touching this original obstacle are at distance 1 of this obstacle, I have a 2, then all these are at distance 2, now I have a 3, and then all of these ones are at distance 3, I have a 4. As you can see, I always have 1 plus of the real distance to the obstacle, because I start with 1 in the obstacles and zeros in the free space. This is why then I have to subtract. Okay, I have to subtract 1 to the final map, and now I have 0 for the obstacle, because the closest distance from an obstacle position to an obstacle is 0. 1 for the one that at the distance 1 using connectivity A, 2 for the ones that are at connectivity 2, and 3 for the ones that are at connectivity 3. Okay, this is the Brushfire algorithm. Very simple to implement, okay? Sorry if I'm not being the most clear possible here, trying to do it online, but it's a simple algorithm. You should be able not only to implement it, but to do it yourself. I mean, if I give you a map like this one, or even a little bit more complex, you should be able manually to do it. It's just a matter of remember what you have at first, and in the end, just to check that you have not made any mistake. It's very simple, because if you doubt if this is a 2 or a 3, you only need to count, okay, which is the closest way from here to the 0. And if 1, 2, 3, and I'm already there, then okay, fine. If you can move in diagonal, 1, 2, 3. Yeah. If you can move only in using connectivity A, then it's 1, 2, 3, 4, 5 at least. Okay. Then it's a very simple algorithm, the Brushfire algorithm, but it's very useful. Okay, because it allows us from any specific map to compute the distance for any cell to the closest obstacle. We don't need to go through all the obstacles or do something more crazy. We just need to grow this, starting from all around the obstacles. Remember that we start all around, let's put it orange. We start from all around the obstacles, okay, for all the obstacles, and we are just growing, expanding this wave, expanding it until we cover the full map. And this is very fast to compute, and in the end we will obtain a result similar to this one. Okay. For instance, here it's clear that the farthest point to an obstacle probably is this region here. Okay. You see this region, and it's at around 60 pixels or 60 distance 60 from the closest obstacle. I don't know which one is the closest obstacle. Probably is this one, okay? Probably is this. This is the 60 that I've measured. Probably is in this direction. Maybe I don't know if here I was using connectivity 4 or connectivity 8. Then I can go in diagonal, or I can only go up, down, up, left, up, left, up, left. But in the end, it's more or less the same. Okay. And here is just a fancy 3D representation of this Brushfire algorithm. Then, why are we going to use that? Okay, if you remember from the equation to compute the repulsion, whenever we need to compute this D, this capital D, now it's super simple, this capital D. If we have pre-computed the Brushfire algorithm on top of the environment, I only need to go to the configuration and see the value of this particular configuration. The output of the Brushfire algorithm will allow me to compute this D super fast. Okay? Then this is what we are going to do, or what you are going to do. Okay? Given an algorithm, given an environment, apply the Brushfire algorithm in order to obtain this map, this map that we have here, and then use this map to compute the distance to any obstacle. Okay, this is an exercise that if you want, you can try to do it. Here I think, just let me see. Yeah, we use connectivity 4 here. Then if we use connectivity 4, let's try to do it. For instance, then for all the obstacles, all the cells that are around this obstacle, we will just take 1 plus the value of the obstacle. Then here will be a 2, 2, 2. Because this is connectivity 4, this is not working. This, yes, 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 yes. 2, 2, 2, 2, and 2. And the same for the one that we have here. Then 2, 2, 2, 2, 2, 2, 2, 2, 2. Okay, we will do something like that. Now, for all the elements that now are error 2, then for all the elements around them, the idea is that we have already added to the L file, to the to the L queue, and then for this one here, because when I added it was a 2, then now I have to put a 3, then 3, 3, and 3, no, because it's all around this. The same for this one, the 4 are already there, and I cannot change it. The same for this one, then only this is new, only this. Let's try to do it. Here I think I have only this. Okay, here the main problem that you can have is forget some value, but okay, we do it all together. I'm quite confident that if I forget something, you will tell me. Okay, yeah, I think that all the numbers that, assuming connectivity 4, are around the 2s, now have a 3 on top. Then let's use now purple. Let's try to put the 4s, then 4 here, 4 here, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. Okay, something like that. Again, I think I should not forget any value. Let's put the number 5s. Something like that. Of course, this is not the way to do it. The way to do it is just to program that and have a computer doing it for you. And let's start again over with the same colors because I'm running out of colors. 6, 6, 6, 6, 6, 6, and 6. Yeah, nothing else. And I'm almost finishing. 7, 7, 7, and 8. Okay, if I'm not made any mistake, I think this should be the solution. Now, the only thing that is missing is that we should subtract 1 to everything. Then this should be a 7, 6, 5, 4. Okay? 7, 6, 5, 4, exactly, yeah? We check what we have there. This should be exactly 1 less than what we have computed. Okay, and you understand why I just subtract 1 to have the correct distance. This is an implementation of the BrushFire algorithm. Okay, it's working. However, it doesn't tell me the real distance to the obstacle. To have the real distance to the obstacle, I have to subtract 1. That is what we have here. Okay. Then, now let me explain you just the motion planning part. Okay, now we know how to compute the traction function. Super simple. Sure. Why subtract 1? Yeah. Here, what I've done is just implement the BrushFire algorithm as, okay, you can find some implementation that already told you that put infinite to the zeros and 0 to the obstacle. This is another solution, and then you just do it and everything works fine. The implementation I was following just says, no, because the normal maps are 0 for free space and 1 for obstacle. You just compute the BrushFire algorithm, assuming that if I'm checking this cell here, then I add this, and this. Well, these two numbers are already in the LQ. In the LQ with a 1, no, because here I have a 1. And then when I remove that from the L, I set here a 2 here, and then I add this one, etc. All the others. But in the end, what you have here, you have expanded, you have applied the BrushFire algorithm, but what you have here is not the real distance to the obstacle, okay? Here, if I look to this matrix, it told me that the distance or the minimum distance from this cell to an obstacle is 2. And this is not true. It's 1, the minimum distance. It's also telling me that the minimum distance of this cell, that is a real obstacle to an obstacle, is 1. And I have to remove. If I just remove 1, take the previous one and I remove 1, I have that the distance from obstacles to obstacles is 0, while the distance from these points to an obstacle is 1, from here it's 2, from here it's 3, 1, 2, 3, here it's 4, 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, 3, 4. Doesn't matter the route you follow, it's the minimum distance is always, okay? As I told you, you will see some books in which the implementation is not just taking the map as it is and adding, it's first transforming the zeros in the map for infinity and the ones for zero, and then applying the algorithm. And then you can avoid the -1 subtraction. Do whatever you prefer. I mean, I don't care one or the other. Both work fine. I just have this implementation in which they just use the map as it is and do not modify it, and then it has to subtract. It's the same. Okay, then now we know how to compute the extractive function. Super simple, just the distance or the distance square. We know how to compute the repulsive function and how to compute the distance from any obstacle. That this was something that can be a little bit more tricky. We know how to add these two functions because it's an addition, nothing else. But then we have to apply the gradient descent in order to go from our current position, that can be any one. Remember that this potential function, you don't care where you start, you only care where you are going to. Okay? Well, in fact, for the repulsive one, you don't care even where you go to. You only care about where the obstacles are. For the attraction, you care where you go to, not where you start. Okay? Then if you change any obstacle, you need to compute again the repulsive. If you change the goal, you need to compute again the attraction function. For the rest, nothing changes. And now we need to apply the gradient descent. I'm sure that you will see, or you have already seen gradient descent in machine learning, and you will see much better than what I want to explain you here. But just the basics, okay? Because here, in the end, we are not going to use probably the real gradient descent, just an approximation. The idea is that when we have this total potential function, okay, that is the addition of the attraction and the repulsive, then the robot needs to follow that, the negative gradient, in order to reach the goal. Okay, this is our goal, what we want to do. We have to be careful, as I told you, there will be critical points. Okay, this will be where the gradient will be zero. Okay, positions in which you reach this position, or maybe because you need to continue descending, but you have an obstacle, and then because of the obstacle is ascending, there is a moment that the gradient is zero. You are not moving, either forward, backward, left, right, you are not moving. This is a critical point. If this critical point happens in the goal, perfect, you have reached the goal, is what you want. But if this critical point happens in the middle of the trajectory that you are following, you are lost, no? You stay there. And then is what I say you here. The critical points can be this maximum, minimum, or saddle point. Okay, if it's the minimum point, the global minimum, perfect. It's where you want to go. But if it's a saddle point or that, or minimum, a local minimum, sorry, then we have a problem. But now let's see how we implement a gradient descent in a discrete environment, okay, in this 2D wall, in this very simple 2D wall, how we can compute this gradient, okay? Basically here I say you, which is the gradient of the configuration AJ, okay? Let's compute the gradient of this configuration that has two dimensions, xy, aj, whatever. And here basically what we do is imagine that we have our wall that is just several cells. Our wall has several cells. Make this bigger if you want. And we want to compute the gradient in this particular point, okay? Then what we have to do is just take this cell here and this cell here, we subtract, and then we generate a vector that can be either here, either here. We don't know if it's positive, if the one in the top is more positive or the other, or whatever. And do the same for this one, and we will generate another one. Okay? Imagine that the value is that this is positive here, and this is very negative here. Then, if we just add these two vectors, this is our gradient descent, okay? This is the one that we need to follow, is this one. Okay, I thought I changed the color. And to compute that is that simple. Is this subtraction, comma, this subtraction. Okay, this will tell us these two small arrows, and then the gradient will be just the vector that points these two arrows. Okay, this is a position, it's a vector. nothing else. Okay, let's see it here with an example. Yeah, imagine that we want to compute the gradient descent in this position. Okay, in this configuration here, that is the 3, 3, 0, 1, 2, no, 1, 2, 3, 1, 2, 3. Sorry, sometimes I start at 0, 0, sometimes I start at 1, 1. Here is starting at 1, 1, then is the gradient at 3, 3. And to do it, we remove the gradient at 4, 3, that is 10 minus the gradient at, sorry, the potential at 2, 3, 10 minus 14, 10 minus 14. This is one side of this vector, and for the other side is the potential at 3, 4, that is 15, minus the potential at 3, 2, that is 9. Then this is our gradient, okay? Because we want to follow the minimum gradient, what we do is just invert that. And instead of moving with a vector pointing minus 4, 6, we move with a vector pointing 4, minus 6. Okay, then 4 minus 6 will be 4, it's positive, it's down, and 6 is left, minus 6 is left, then we will move around this direction. Okay? We are not going to move minus 4 positions and 6 positions. We are just going to move a step towards this direction, okay? This is the gradient that we have to follow, but then normally, and this happens with all gradient-based algorithms, we don't follow the full gradient. This gradient can be much bigger or can be much smaller, but we don't follow the full gradient. We just follow a smaller step towards this direction, okay? Because now we are living in a discrete world, most of the times we are going to use this gradient approximation, okay? We are not going to follow the real gradient. We just want to move one cell. Then we don't care if it's minus 4, 6, or it's minus 1, 2. We just care about the direction, okay? We have these 8 directions around the current position, and we want to know, I move left, right, up, down, up, right, up, left, wherever I have to move. And then for that, we can just follow this very simple algorithm. From the current cell, compare its potential with the 8 neighbors, okay, do like subtractions. Select the neighbor with the smaller potential value, and then this just is a value, it's not a direction, then just move one step in that direction, in the direction of the neighbor with the lowest potential value, okay? And then this step will be your 1, 0, or minus 1, 1, or 0, minus 1, whatever, okay? There are 8 different combinations. And this is an approximation of the gradient, because we are not using the model of the gradient, okay? Sometimes the gradient will tell you move very fast in this direction. Sometimes the gradient will tell you move very small in this direction. If you do that, you lose this, okay? You lose this magnitude. You only have the orientation, at which direction you have to move, but not how far you have to move. But for most of the algorithms, it's more than enough, okay? A small, the same values, okay? An example here, this is our potential function, okay? Whenever you have done the attraction, the repulsion, everything, you obtain, this is a patch of the map with the values. Then I just do the subtractions for this part here, okay? I just subtract I compute the gradient, not this with this, but just the center with any position, okay? The center with any position. And I see that the one that decreases the faster is this one. Then this is the direction I want to follow, and this direction is 1, minus 1. 1, it's down, minus 1 is left, then down left, okay? This is the direction I want to follow. The first is the x here is the vertical, the number of rows, let's say. And the second dimension is a y, that is the columns. Columns left, columns right, so negative, positive, and positive, negative, and this is this direction. Okay, here, just be warning, because now I want to show you the algorithm, and the algorithm told you that you have to follow the gradient minus the gradient, okay? Well, we have just done here, that is follow the gradient negative, okay? We obtain this gradient, but we follow this. We follow the gradient negative. Here, no. If you do that, you already are pointing to the smaller one, then you are following the negative gradient. Then don't forget to remove the minus, okay? And this is the algorithm, okay? The algorithm says, just initialize here, just to recap a little, the gradient descent will be applied when you have computed the attractive function and the repulsive function. You have added together. You know which is your starting position, and you know which is your goal position. You know where it appears, some place it has to appear, the goal position. Okay, and it's done or it's used. Sorry, to compute the trajectory that you have to follow. That is basically the trajectory will tell you which is the path in which the gradient is decreasing. Okay? Then you will initialize your initial configuration will be the starting position. You have to define this is the step that you want to do in the direction of the gradient, and this is just to check that you are not getting stuck in a local minimum and you stay there forever. It's a good practice. While the gradient of the current configuration is bigger than epsilon, remember if the gradient is 0, we are stuck because we have reached the goal or because we are in a saddle point or minimum, something like that. Because we don't believe a lot with exact numbers here, we always say if the absolute value of that is slightly bigger than 0, epsilon should be a very small number. And we have not reached the maximum number of steps. Again, it's just a safety thing to avoid getting stuck. Then we compute the gradient. We have seen how to compute the gradient of the function u. We have seen how to compute the function u at point qi. Qi is the current point. Okay. Then we update and we say, okay, the new configuration, the qi plus 1, will be the previous configuration minus, here is where you are following the negative gradient, okay, because of this minus, and a step size that you have to define here between 0 and 1 normally, of the direction of the gradient. What means? If you start at position 3, 3, for instance, remember in this, let me put it in this example, no, we are in this position, that is position 3, 3. Imagine that our step size is 0.1, because we are following the gradient 4 minus 6, then the new position will be 3.4, 2.4, okay, because at one we have added 0.4 and in the other we have added minus 0.6, okay, step size 0.1, direction 4 minus 6, then we have to add that to this 3, 3, okay. Again, if we do that in a discrete world, we end up in the middle of two cells, and this is why most of the time we just use a simplification like this one. But if we do that, we don't have to define a step size. Step size is always move one cell, and we don't have to add the minus because we already are following the gradient descent. Okay. Then we compute the new position. Here we compute the new position. If the new position sorry, I think, okay, if we have not moved at all, the current position is equal to the old position, or almost the same, okay, this is again, it's like epsilon, it's a very small value, or the potential in these two things, it's the same, again, we have reached a local minimum, just safety checks, okay, then we break, otherwise we increase 1, then minus 1, and we stop. And this function will end not when we reach the goal, when we reach a position of 0 energy. That can be the goal or not. Okay, just let me show you a couple of examples and then we continue. Imagine we take the function, the potential function that we have generated before, that is the addition of the attraction function plus the repulsive functions. In this function is the same, seen in 2D. Okay, the only thing that is different is that I've marked here the goal and in red, and the starting position in black, and then I apply gradient descent. If I apply gradient descent, I obtain something like that. Oh, it just works. But what happens if I modify the initial and final position? Same environment, of course, same repulsive function, because the environment is the same, those tables are the same, but because I've moved the goal, the full attraction function has changed a little, and I pick up a different point, okay? Probably from here I pick up this point, it will work. Also, okay, I know this one, it will work. But picking up this starting position, what happens is this. I start following the minimum descent until I reach the zone in which I get stuck, okay? And I cannot get from here, okay? The road will be here, maybe it will move a little bit up, a little bit down, but it will not move any farther of this point. To just to recap a little bit, okay? What we have done here, no, is first to learn to compute the attractive function that we have seen that is super simple to compute the attractive function. We have seen two of them, the linear one and the quadratic one. Then we have seen how to compute we have seen how to compute the recursive functions. Again, it's super simple, but in order to compute the recursive function, it's true that we need something that can be not so easy to compute, that is the distance to any obstacle. For that, we have seen that the BridgeFire algorithm can make it. Then we have seen how to combining these two functions, we obtain a total function, and then we can just follow gradient descent in order to reach from any position to the goal position. Problem, sometimes we get stuck. Then let's see one way. Well, I will present you two ways, but the most important, or the one that I want you to focus more, is in the first one, because it's the one that you will be asked to implement to avoid that. Okay, how we ensure that the potential function, or the total potential function that we are computing, has only one global minimum, okay? One minimum. This is, if we can ensure that, we're happy, because then we just follow gradient descent and we reach the goal always. But how we can ensure that? There are two ways to do that, okay? One way is just, let me start from the second one, is using a special set of potential functions that ensure that, okay? Ensure that there is only one minimum. And these functions are called navigation functions, and they are not so simple to compute, okay? Again, here it has evolved a lot, this topic, and probably you can find papers from the 90s or the beginning of 2000 in which there was a lot of people trying to find and different ways, different algorithms to implement navigation functions that guide you always. But then new algorithms, completely different algorithms, that are the ones that we will be looking during the next classes appear, and this gets a little bit less attention and it's less popular. However, there is another that is, a wavefront planner can be seen as one of these navigation functions, because exactly that, generates a potential function that has a single local minima. Then, by definition, it matches. We can say that the wavefront planner is a kind of navigation function, although it's not exactly the same. You will see why. But this is a super simple algorithm, and it works. Okay, it has some. It's very simple, and it cannot be used always, all the time. But most of the time it can be used, and it works, and it's super simple, and in fact uses the same idea of the BridgeFire algorithm that you have already seen. Then it will be quite easy for you to understand. Then let's try to see first this wavefront planner. Some of the simplifications I was telling you is a grid-based path planning algorithm. Okay, for us, that we are assuming that we are in a 2D world, in which the wall is known a priori, in which everything is discretized to 2D, in which goals are just XY positions, in which our robot is a point, that also the configuration space is just XY. It's perfect, it works. It's true that for a real robot that moves in a continuous wall, maybe with much more degrees of freedom, etc., maybe it's not the best algorithm. But for us, it will make the job. The idea is that in the previous algorithms, I told you that we care about the goal because of the attraction function, that we need to attract towards the goal, and we care about the obstacles because of the repulsive functions. Okay, here what we need to do is to compute a path again from the goal, but that expands all over the environment, avoiding the obstacles. And it does everything all together. And it's not two different functions, an attraction and a repulsive, that just are other. It's just a single function or a single algorithm that compute this potential field. It's a kind of potential field, because by each configuration it tells us the potential. Okay, then computes this, that combining everything. And as I told you, it's from the same family of the BridgeFire algorithm. It's just expanding away. The results will contain this, that the number of minimum steps to reach the goal. Okay, this is the result of the algorithm, and this is what can be seen as a potential function. Okay, And therefore, we can apply, if you want, the same gradient descent that we have seen before, and it will work. Okay, here I put you just this disclaimer, no, that the width component is not a potential field method per se, because it's not attractive repulsive function. Conceptually, it's the same. Okay, it's why I explained you it here, and because it generates this scalar field. Okay, that in the end is what we want, is for each configuration to know how far I am from the goal and which direction I have to follow, and just follow the minimum gradient direction, and it will work. But although it's very similar, conceptually it's very similar, it is not a real potential function. That just let's try to be rigorous, no, and say the things for its name. Remember, what we're trying to do here is we have a map, the grid map, in which we have some obstacles and we have a goal. And regarding where we start, we want to find a function. In this case, more than a function, it will be this distance map. It will be for each cell, it will tell us how far we are from the goal. Then, if we are in any particular cell, we only need to check all the surrounding cells and see which is the smaller value and move to this cell because it will be closer to the goal. Okay, this is the main goal of this wavefront planar algorithm. Then the idea is, because in the end what we want to do is to return this distance map, this dm. Also, I changed that here. I think in the previous slide I put d, but because d is also the distance to any obstacle according to the other function, just to do not confuse you, I changed this d for dm, sorry. Then what we want to do is to return this distance map. We initialize all the free cells, not to 0, but to the maximum value. How you can compute this maximum value? It's pretty simple. Imagine that you have 10 rows and 20 columns, then 200. There will be no cell that is farther than 200 from the goal. Okay, even if you have to do a full spiral, no, and you start from the farthest area, it should be never bigger than that. Then you can safely initialize all the free cells to this next value. But of course, this value, even if it's very big, it will be always smaller than infinite. That is the value that you will put to your obstacle. This can be in a lot of different ways, and I think here my confusion is because I used to do like 2 distance maps, one that checks if it's visited or not visited, and one that contains the real value. But I think that now, as it is right now, with a single distance map, it's enough, and you have all the information there, and then probably it's simpler. Then whenever we have initialized that, we just take the goal, the cell, Q goal is the cell that contains the goal. Right? This can be imagined an XY position or AJ position. And we set this position in the distance map to 0 and add the position, not the 0, the position of this Q goal to the Q. Okay, Q is this Q, it's a Q called Q, then we add this here. And then while this Q has elements, initially we'll have only the goal, but we will see that we will be adding new elements to this Q. What we do is pop up the element from this Q. This means pop, it's always meaning from the beginning. And then for each neighbor n of this T, then this is, if we start imagining that our goal position is position 5, 5, then for all the neighbors of the cell 5, 5, okay? And here when we talk about neighbors, we can assume connectivity 4, that is just the cell on top, down, left, and right, but we can also assume connectivity 8, where we have 8 neighbors for each particular cell. This is up to you. Then for each one of these neighbors, what we say is, if the cell that corresponds to this neighbor is not infinity, it means it's not an obstacle. We want to propagate the wave on top of obstacles. And if it's different of an obstacle and the value of the cell is bigger than the value of the cell I'm coming from, the beginning will be I'm coming from the goal, because goal will be the only element in the Q. Then if it's bigger than the goal plus 1, then the idea here is I reach cell n with the distance indicated to the distance map. Then if I can reach this cell, sorry, the cell T with the distance in the, wow, this is another typo. This is DM, eh? I see it now. Sorry, this is DM, eh? When I change it, I forget to change this one. Then, if you are able to reach cell T with some distance, the one that specifies here, then you should be able to reach cell N with this distance plus 1. Therefore, if this value is bigger than that, you don't want this value. You want to replace it by, again, sorry, this is DM, always typos. I will check that later in the slides, but just that. You will replace it for this new value. And then the other thing that you have to do, very important, is to add this neighbor to the queue. And this is the way that the waveform is followed. Okay, then in order to follow the path, whenever we have generated this function, this is this potential function, but this function, okay, this how I put the exact name, sorry, the scalar field, when we have built this scalar field, it's almost the same as the potential function, we need to follow the gradient descent. Here, we will always follow a gradient descent in which we don't use the real gradient, but just this discrete that we check around and we see which is the cell around our current configuration that has a smaller value, and we move one step in this direction. Then again, it's not a real gradient descent, but it's the same concept. Okay, just looking around in this particular position, looking around, see which is the direction from the 8 available directions or the 4 available directions that decreases this potential field, the more, and we just move this direction. That's okay. And this is the algorithm that, okay, it's just a greedy version of the standard gradient descent, but for moving in a cell, okay, moving step by step in a cell. Let's see an example, okay. Let me try to make it here. Again, let me see if I use, I use distance, connectivity 4, just to make it like you have in the solution. Okay, then the idea is that we start here in the 0, then we say D of this particular cell is 0, and we add this cell in the Q list, in the QQ, sorry. Then I remove this position from this queue, and for all the neighbors, because this was 0, then I add 0 plus 1, then I add here 1, 1, 1, and 1. And I add these 4 cells also in the queue. Then we take this 1 from the queue, I check all the neighbors. If the neighbors are bigger, if the neighbors are smaller, check this is 0 and this is infinite. If they are smaller or are infinite, I just do nothing. But if they are 0 in unvisited, let's say, if they are unvisited, then I just put here a 2 and add this 2 in the configuration, in the QQ. The same from here. For this one will be this and this, for this one and this, and for this one only this, because the others are already there. Okay, sorry, let me do this in a different color, otherwise we will see nothing. Let me just 2, 2, 2, 2, 2, and 2. Okay, now for the next one, again, I remove these 2 because all the surrounding cells here are already or infinite or has a smaller value. I do nothing. For this one, yes, I can add this, 3. This will be a 3. Okay. For this one, this and this. For this one, this and this. Doesn't matter much, okay? The order is important for layers, let's say, okay? If you start one layer while you have not finished the previous layer, then you can have some problem. But inside the same layer, doesn't matter if you start for one or for the other. Okay, then another one. Now here, 4, 4, 4, 4. All them will be 4s. Now 5, 5, 5, 5, 5, and etc. I can continue, but I mean, I think you get the idea. It's nothing. Okay, it will be expanding. The idea is that these lines, that here we start at 0, Then we do this line here, this wave, sorry, this wave here, this wave, yeah, sorry, this one is moving like that, this wave here, this other wave here, this other wave here, this other wave here, etc. That we are expanding using this wave. This is the idea that you have to get. And these waves eventually will reach all the places, okay? Will reach up to here. Of course, to reach it here, I need to do lots of expansions, you see? I need to do 15 expansions to reach this specific area here. But now that I have that, I can start from any place again. Here, I don't care where we start. When we compute the wave planner, we only need, like before, the obstacle and the goal. The goal, yes, has to be clear. But now I can take these positions, for instance, and saying, okay, from these positions, from these 15 here, which is from the surrounding, which is the smaller one. If we assume that we have connectivity 4, I cannot pick up the 13 because I cannot see it. I have 14 and 14. I don't care. Then let's assume that I move this side. Okay, here I have 13, 13, 15. If I go back, no, then I can pick or down or right. Let's imagine that I pick right. There is a lot of times in which I have multiple choices that have exactly the same value. It is because the path that I will obtain is exactly the same in cost, okay? Assuming that the cost is one step each. Here I will follow the 12, 11, 10, 9, 8, and here you see if I continue moving right, it increases again. Then I cannot move right. I have to move down. 7, 6, 5, 4, 3. Again, if I keep moving down, I increase. Then I have to move left. 2, 1, 0. Okay, I found a path from here to here. You see, if I was applying just minimum descent, then probably I will just try to move to this direction, and then here maybe we move a little bit down, but then the 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 potential, the gradient of the potential will increase, and then I will end up with some local minima. Here, no, there is no problem. I can follow that. And if you follow any other path, if instead of here, you follow 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then 0, that is a different path. Sorry, I do it in the same color and probably you see nothing. Just this one, I mean. If you follow the green path instead of the red path, you will see that it contains exactly the same number of steps. And it doesn't matter which path you follow, that you will always reach the minimum position. Okay, then this is the idea of the wave from planar, okay? Obtain potential field. It's not a potential field, but it's this field of values that just going always towards greedy, in a greedy way, towards the one that is smaller from all your neighbors. You will always reach the goal, avoiding the obstacles. Let's see in the map. When we look at the map, the same initial position and final position goal that we have at the beginning, then this is the configuration we have followed. I think here I was using connectivity 8, okay, because otherwise, I don't know, but you have these very nice diagonals, okay? And here is the problem that we used to have, that if we just follow gradient descent, it moves towards here and it gets stuck. And now what happens? That it already knows that and it just follows. One problem that you can see with the wave from planar is that it likes a lot to pass super close to the obstacles. Okay? And this is something that is good because it means that this greedy and this path is the better, that you cannot find a better path than this one. It's optimal. Okay? Remember, what we told that if there is a solution, it has to find the solution, it is complete. If the solution is the shortest path that you can find, then it is optimal. Okay, then it tries to be optimal because it always chooses the smaller path, but if you have an expensive robot, probably you will not, and this is not a wall, or is a wall or whatever, but you don't want your robot to be so close to this obstacle, then it's a hole in the floor. then we can do several things to avoid that. The most simplest one is we just take the original obstacles and we just expand them. Okay, remember again in the configuration space lesson that we did at the end of the last week, in which we say that sometimes if we have a robot that can be approximated to a circle, we just expand the obstacles by the radius of the robot, and then we ensure that all the positions that now the purple positions here, the data free positions that are free for a point, for an XY point, are also free for a robot that is 35 centimeters diameter, something like that, no? Kind of that robot. Then one way to avoid our wave planner to be so close is just doing that. The other way is combining the wave planner, the output of the wave planner, with the repulsion function. Okay, you can do things like that. It can be more dangerous. Okay, if you start doing things like that, for instance, here it used to be a path here, and now this path has been blocked. Okay, you see this path here. We have a path here. Now the path is blocked. However, if you come, because we have first expanded the obstacles and then computed the waveform planner, it's not a problem. The waveform planner knows that now this path is blocked and it's not trying to move you here. If you first compute the waveform planner and then you expand the obstacles or you add a repulsion function or something like that, the waveform planner can ask you to move through this path, and the path is not anymore existing. Then you have to be careful. Okay, it's better to first modify the environment and then apply the waveform planner than doing the other way around. Another exercise. Okay, I will not do it, but you get the idea, and you have here you don't have the solution. Okay, better for you. Then you do it at home and see if you are able to do it. And then just a few words about these navigation functions. Okay, this is the full description, okay, that is specially designed potential function. These are really potential functions, not like the waveform planner that is a kind of, but it's not a real potential function, using motion planning to guide the robot towards the goal. Okay. What I want you to understand is this key property. Is that they avoid local minimum. And how they avoid local minimums? Because they are constructed in a way that there is only one minimum, one real minimum, okay? And that everything moves towards the minimum, similar to what the wavefront planner does, but now using really potential functions. Okay, and the idea is this one, that the potential functions decrease smoothly towards the goal, ensuring that no other minimum exists where the robot might be trapped. Okay, this is one paper, maybe it's the most famous one, and as I told you, it's pretty old. Okay, that is why I introduced. We just explained you this exists. If you has to be used, if you have to use that sometime, just take this paper. In general, when you, for papers, no, it's something unrelated there, but it's very important where these papers are published, okay? For instance, IEEE is a well-known place to find papers, no? But you have Elsevier, you have IEEE, SAGE, there are lots of different places in which you can find papers, but inside IEEE, there is thousands of conferences, of journals, of everything. Normally, journals are qualified in quartiles: Q1, Q2, Q3, and Q4. Okay, the journals that are Q1, Q2 used to be good journals in which people that do serious research publishes. Q3 and Q4, okay, or there are very preliminary works, or are students' works that maybe are not the best, etc. In general, all transactions in IEEE used to be good journals, okay? Used to be Q1, Q2. And I know that there's actually on robotics. This is on robotics and automation. Probably names have changed from the 92. Now there is the next robotics and transactions on automation. But transactional robotics used to be very good papers nowadays. If you find a paper in transactional robotics, used to be a good one and difficult to publish. I mean, because now you will have to start looking to papers to do things, to do work, then it's important just to see where the paper is published, see how many citations the paper has. Okay, these things tell a lot about the paper. Sometimes I ask the students to do a project about that and check for some papers, and they show me papers. That is the first one that maybe Google shows you, but that is not a good paper. And it's very easy to see if a paper is good or not, just looking where it's been published, the reputation of the journal, how many citations the paper has. Okay, stop the parentheses. This is an example of a navigation function. Okay. For instance, here the environment is a circular area, and here we have 4 obstacles. Okay, and the goal is to reach just the center of this bubble. Okay, and here there are different implementations with but local minima and others that have no local minima. Okay, here you have some local minimas. Here. Well, here everything moves you towards the center of this bubble. Okay, to do that, to reach the goal without getting stuck, this is the most important. What we need to ensure is that the goal has the minimum value possible, normally 0, that the both obstacles and the walls mean the perimeter, okay, the perimeter has a high value, it can be not infinite, sometimes this is just something between 0 and 1, then 1 if you want. And then everything in the middle, here obstacles and the work scale is boundary, the two things. And then everything in the middle is smoothness and continuous. And here is one of the most typical functions that they are using in order to compute these navigation functions that are called the harmonic functions. Okay, I don't know if you are good in control, maybe you have used this harmonic function. I'm a computer science and I'm not super familiarized with them. But then the idea here is that these functions have no local minima or maxima inside the free space. Okay? And then the idea is that set this function when this function is in the global configuration, it has to have value 0. And when it's in an obstacle or in a boundary, it has to have value 1. And then in the middle, we just do a kind of a smoothness for all the neighbors. And then this is the idea that we will start, I think here in the algorithm, maybe it's even easier to see. This is the same, but in an algorithmic form. Okay, we set up goal to 0, set up boundaries and obstacles to 1. For the rest, we initialize it at 0.5, but then we smooth that. And in order to smooth it, the only thing we do is we take the old value and we compute the new value just adding all the 4 cells, the top, the down, left, and the right, divided by 4, then an average of all the places, and we check if the previous value and the new value has changed. If they have changed, if this is bigger than whatever is in this delta, that initially was 0, but we will do that for all the cells. And basically, at the end of this 4, we will have moved through all the cells and stored in this delta the cell that has changed the most. When the cell that has changed the more has changed almost nothing, it means that we have smoothed the full trajectory. Okay, this is a very naive way to implement a navigation function, but that more or less works. Okay, with some issues that may happen, but it can more or less work. Okay, for a simple environment. Again, here there is a simplification because we are using this for a grid environment, while the nice thing of navigation function is that are continuous and therefore they can work not only in this grid environment. Okay, but as I told you, this is just a small introduction about what a navigation function is, and what I want you to be able to implement is the wavefront plan. This algorithm, okay? Not the other one, this and this especially.